Okay, so this is 2013 Level 3 Mechanics, Question 3, Oscillating Balls, Simple Harmonic Motion question essentially. So we've got a pendulum, length 1.20 metres, set of motion swinging backwards and forwards. Like pendulum, because it is a pendulum. A, show that the period of pendulum of length 1.20 metres, 3 significant figures, that is oscillating in simple harmonic motion is 2.20 seconds. This is a case of using the formula for the pendulum, 2 pi square root L upon G. L is the 1.20 metre length, G is 9.81 metres per second squared. B, explain what must be done to ensure that the motion of the ball approximates simple harmonic motion. Remember, simple harmonic motion, the restoring force is proportional to the negative of the displacement. So you have to maintain that condition basically, and for a pendulum it must have a small angle. Yeah, that's kind of the essence of it. C, let's just move down. On the axis below, sketch a graph to show what happens to the ball's total energy over time until it stops swinging. You're probably used to simple harmonic motion questions. They get you to sketch the amplitude as it over time for a damped simple harmonic motion. We're not interested in the amplitude at all, we're interested in the total energy. So the total energy will follow that same decay envelope, so it'll be an exponential decrease over time. Because obviously the total energy is the sum of the kinetic plus the potential energy. And yeah, at the start you've got the maximum amount of that. It doesn't matter where on the amplitude you are, the total energy is always going to be a sum of both of those, and friction and other internal forces in the string, which can all be summarised as friction, are gradually taking energy away exponentially. There we go, moving on. We don't need to explain it. Let's try and be a little bit quicker. D, it is possible to get the ball swinging by holding the top of the cord and gently shaking it backwards and forwards. Explain how shaking the top end of the cord can make the ball on the bottom of the cord oscillate in simple harmonic motion. And your answer should consider resonance and energy transfer. So obviously, if you're taking the top of the spring and shaking it backwards and forwards, you're transferring energy to the pendulum to make it do that. If you move it that way, the pendulum is going to swing across and follow. If you move it back that way, the pendulum is going to swing across and follow. What you have to do to transfer your energy from the motion up here down into the pendulum bob here is to swing at the resonant frequency. So you have to swing it at the resonant frequency, and this way the natural frequency of the pendulum, you will be applying a push in the direction that it is needed for it to increase the motion. Remember, we call it driven simple harmonic motion or resonance, and you're increasing frequency. If you were to push someone who's sitting on a swing and they were coming back towards you, and you applied a force as they're coming back towards you, that's damping it, that's not at resonance. But if they're going away from you and you help it along its way with that force, you're pushing with the frequency of that swing and making it increase in motion. Okay, got to carry on. E, simple harmonic motion requires a restoring force that changes in proportion to the size of the displacement. F equals negative kx, we've seen that. Discuss what provides the restoring force. This is key to the whole thing. When the ball is swinging in simple harmonic motion, in your answer you should describe what forces act on the ball. Let's do it really quickly. We've got the tension force in the string, and we've got the force due to gravity. Those are the only two forces acting. Explain how these forces change as the ball swings. Well, the force due to gravity is constant, but the tension force is going to change. And excuse me, if this is where we have to get into point 3 as well, draw vectors to show how restoring force is produced. The temptation for this is to go back to your conical pendulum situation where the force due to gravity balances out the vertical component of the tension force. Okay, and then the horizontal component of the tension force provides the centripetal force. But it's not that situation, it's not the same thing. You can't use that analysis of it. What you do need to do is look at it this way, that your gravitational force force due to gravity, is going to be broken up into components. Okay, this is just a little bit, this is a simple harmonic motion construct. It's really important to remember that that's how we do it. Still right angle triangle, but our force due to gravity is broken up into our restoring force and our negative tension force. So here's the ball here. You've got that real force due to gravity acting on it. You've got that real tension force acting on it. I've drawn it too big, but this bit of the gravitational force is going to balance out that tension force. So as the pendulum swings higher and higher, eventually, well, you've got to be careful because we're supposed to use a small angle approximation, but for the purposes of this, I'm going a little bit bigger so you can see it. But as that amplitude increases, the force due to gravity is acting downwards, and there's less that is acting on the angle, less of that that's opposing the tension. So the tension force has to be decreasing. Tension force has to be decreasing as it goes on, that matches what we know, because that remaining part of the force due to gravity acting in a tangent to here's a pendulum bob, acting in a tangent to it, causing it to accelerate back towards the centre. That has to be increasing the higher it goes. Otherwise, your simple harmonic motion condition, where the restoring force is proportional to the displacement, the negative displacement, because the force is going back towards the equilibrium position. Otherwise, that condition won't be true. Okay, so hopefully that helps you, but the real key for this is that construct where we view it from perhaps the frame of reference of the ball, where up is in the direction of the tension force, and then down is kind of that component of gravity which balances out the tension force. That means there's a tangential force sideways, if we were to draw it on top of the ball, which is leading it back towards the centre. And remember, for very small angles, this is for very, very, very small angles, so that tangential force can be approximated to be, rather than at an angle, to be just going linearly back and forward, back and forward, back and forward. There you go.